Have you ever looked at a system and thought, that could be so much more efficient? We're obsessed with optimization, cutting waste, and maximizing output. Extra capacity looks like a waste of money. Redundant processes seem pointless. Slack time feels like laziness. From the perspective of pure efficiency, resilience looks like a problem that needs to be solved. Efficient systems are designed to get rid of anything that doesn't directly contribute to the final product. They minimize idle time, eliminate duplication, and push for maximum utilization. The result looks clean, streamlined, and incredibly productive. Yet, when these finely tuned systems face stress, uncertainty, or a sudden change, they are often the first to break. So, why does the very thing that makes a system robust and durable look so inefficient? To understand this, we need to look at how systems behave when things don't go according to plan. Efficiency is all about optimizing for what we expect. It thrives on predictability. Systems are designed to perform perfectly under expected conditions, assuming stable demand, reliable inputs, and very little variation. Everything is tuned for the average day. This works wonderfully, as long as reality plays by the rules. Resilience, on the other hand, is concerned with what happens when reality throws a curveball. It's about preparing systems for rare events, unexpected disruptions, and situations we've never seen before. Because these events are, by definition, infrequent, the investments we make in resilience can seem completely unnecessary most of the time. One of the cornerstones of resilience is redundancy. Resilient systems maintain backup resources, alternative pathways, and spare capacity. From an efficiency standpoint, this just looks wasteful. Those backup generators sit unused. The extra server racks produce no output, but redundancy isn't there to improve daily performance. It's there to absorb shock. When a primary component fails, that redundancy suddenly becomes the critical difference between a quick recovery and a complete collapse. Unfortunately, standard efficiency metrics rarely capture this hidden value. Another key element is slack. Slack is the breathing room in a system. It's the unscheduled time that allows people to pause, think, reallocate resources, and adapt when conditions change unexpectedly. It supports human judgment and creative problem-solving, but efficient systems are designed to eliminate slack. Every resource is tightly scheduled, and utilization is pushed to 100%. There's simply no margin for error. This boosts short-term output, but it cripples the system's ability to respond to surprises. When an unexpected demand arises, there's no flexibility left. Slack looks inefficient because it might reduce measurable productivity on a normal day, but it is absolutely essential for adaptation when things go wrong. This brings us to human judgment. Resilient systems rely on people. They depend on individuals noticing anomalies, interpreting complex situations, and making decisions that can't be pre-programmed into an algorithm. Judgment is often slower and less predictable than automation. In the quest for optimization, we often try to constrain judgment with standardized processes, automation, and rigid rules. Decisions get encoded into the system, and any deviation is discouraged. As we remove human judgment, systems become faster and more consistent, but they also become far less adaptable. Resilience looks inefficient because good judgment can't be optimized in the same way a manufacturing process can. Resilience is also built through learning, and learning requires a tolerance for imperfection. To truly understand its environment, a system needs to experiment, get feedback, and sometimes fail. Efficient systems, however, are designed to minimize error at all costs. Mistakes hurt performance metrics and increase costs, so experimentation is often shut down. This might reduce short-term risk, but it also starves the system of opportunities to learn. When conditions inevitably change, the system has no experience in dealing with anything unfamiliar. Resilience appears inefficient because learning is a slow, messy, and unpredictable process. Ironically, the most highly efficient systems often appear to be the strongest. Their metrics are perfect. Processes run like clockwork. Output is consistent. From the outside, the system looks incredibly stable. But this is often an illusion that masks deep fragility. Because all variation has been engineered out, weaknesses can accumulate silently beneath the surface. The system performs flawlessly under normal conditions and then fails catastrophically under the slightest stress. Resilient systems, in contrast, tend to expose their weaknesses earlier. They reveal inefficiencies, delays, and imperfections along the way. This transparency can make them appear less capable, even when they are fundamentally more robust. Efficiency also tends to favor centralization. Centralized systems reduce duplication and improve coordination. Decisions are standardized, and control is consolidated in one place. Resilience, however, often benefits from decentralization. Distributed systems allow for local, context-specific responses. They reduce single points of failure and enable faster adaptation at the edges of the system. Decentralization looks inefficient because it can introduce inconsistency and overlap, but that's precisely what increases its ability to handle diverse and changing conditions. Think about the philosophy behind each approach. Efficient systems focus on preventing failure. They optimize processes to reduce error rates and eliminate all disruptions. Prevention is measurable and very appealing to managers. Resilient systems, however, assume that failure is inevitable. They focus on recovery rather than the impossible goal of eliminating all risk. They invest in the ability to absorb shocks and restore function quickly. This approach seems inefficient because you're allocating resources to events that might never happen. Its true value only becomes visible when prevention fails. Even time is treated differently. Efficiency values speed above all else. Faster processes reduce costs and increase throughput. Any delay is seen as a bottleneck to be eliminated. Resilient systems, however, often build in time buffers. They include checks, pauses, and waiting periods that might reduce raw speed but dramatically increase reliability. These buffers stop errors from cascading through the entire system. They look inefficient when you're just measuring throughput, but their value lies in preventing a total collapse under stress. This relentless focus on efficiency can create a dangerous sense of overconfidence. When metrics look strong, it's easy to believe all risks are managed. Leaders start to see redundancy and slack as unnecessary fat to be trimmed. This confidence discourages questioning. Warnings get dismissed, backup systems are dismantled, and safety margins shrink. Overconfidence grows precisely as resilience is being eroded away. Resilient systems, by contrast, maintain a sense of humility. They assume uncertainty is a given and actively prepare for surprise. But humility looks inefficient in a culture that rewards absolute certainty. In competitive environments, the pressure is immense. Efficiency is rewarded, and costs must be minimized. Short-term performance is what gets you ahead. Investments in resilience, which reduce visible short-term performance, are penalized. Organizations feel forced to eliminate redundancy, slack, and discretion, making their systems leaner but also more fragile. Resilience appears inefficient because its benefits are often delayed and uncertain, while its costs are immediate and obvious. Perhaps the biggest challenge is that efficiency is easy to measure. Utilization, throughput, and cost give you clear, hard numbers. Resilience, on the other hand, is notoriously difficult to quantify. How do you measure preparedness, adaptability, or recovery capacity? These things don't produce continuous output. They remain invisible during normal operations. Because resilience lacks clear metrics, it's consistently undervalued, and what we can't easily measure, we tend to dismiss as inefficient. Ultimately, efficiency and resilience are optimizing for completely different goals. Efficiency aims to maximize performance under known conditions. Resilience aims to maximize survival under unknown conditions. When we confuse these two goals, we end up building incredibly fragile systems. Optimizing exclusively for efficiency strips away the very features that enable recovery and adaptation. So, resilience looks inefficient because it's not trying to win the same game. It requires us to accept a certain level of inefficiency as a deliberate design choice. Redundancy, slack, decentralization, and human judgment aren't mistakes to be corrected. They are essential features for long-term survival. The systems that endure over time are the ones that accept this cost. Those that don't appear incredibly efficient right up until the moment they fail. Resilience is invisible until it matters most. It consumes resources without producing immediate, measurable output. It prepares for events that may never happen. While efficiency dominates our dashboards and reports, resilience works quietly in the background. But when stress finally arrives and conditions change, the efficient systems break, while the resilient ones absorb the shock, adapt, and recover. The difference isn't in their daily execution, but in their fundamental design. Resilient systems aren't inefficient by accident. They are inefficient by necessity. Thanks for watching. If this idea changed how you think about efficiency, consider liking the video and subscribing for more content that challenges conventional wisdom. See you next time.